Hey guys, in this video we are going to talk about 7.1, integration by substitution. And this is actually going to be the last topic we cover in Calc 1. Alright, so last week we talked about finding antiderivatives and indefinite integrals of simple functions such as f of x equals 3x squared. So the way that we did this was we added 1 to the power and divided by whatever we got when we did that. So this guy is just going to be 3x to the 3. And actually we could take out the 3 if we wanted to. Should have a dx. And so what we ended up getting, we got 3x to the 3 over 3 plus c. All right, we added 1 to the 2 in the exponent, and then we divided by whatever we got there. So we know how to do that. But what if we have something that looks like this? Well, this is quite a bit more complicated, right? Now we don't have a nice simple polynomial function, but we have a square root involved. We have a function times a function. And so the way that we can deal with these is with substitution. And I'm going to show you how to do this. Okay, so let's just do it step by step. So to tackle problems like these, as I said, we need to substitute something. We need to introduce a new variable. And typically you're going to see this done with a U or a W. I like U better, so that's what I'm using here. I think your book might use W, but the idea is to replace something in the original integral that is easily differentiable. So, and it takes some practice to see what this is, but 9 out of 10 times, if you have a square root, what you're going to be subbing u equal to is what's under the square root. All right. So in this case, I'm going to say, let's let u equal to 1 plus x squared. And so step 2 is we're going to take that substitution and we're going to take the derivative of both sides with respect to x. So on the left, we have, if I take the derivative of u with respect to x, I just get du dx. And if I differentiate 1 plus x squared with respect to x, I just get 2x dx dx, which just goes to 1. All right. Then what I'm going to do is I'm going to figure out what, and this should actually say, let's see. This should actually say isolate dx. So we want to see what is dx equal to, because the idea is that we want to get this integral in terms of u, and we want to integrate with respect to u. All right. And so maybe I'll just stay up here while I do this. If we isolate dx with this equation that we just found, we end up getting that du is equal to 2x dx, first by multiplying dx on both sides. And then what I can do is I can divide both sides by 2x to give me that dx is the same thing as du over 2x. And so I can make that substitution right here. So I'm going to erase some of this, so just bear with me here. I'm going to just erase all of this, so just forget about that. Forget about this. Forget about that. Forget about all of this. All right. Okay. Let's go back up. Okay. All right. So far we have u is equal to this and dx is equal to this. So I'm going to sub in these values into my original integral. All right. So what was my original integral? Well, I had 2x times the square root of 1 plus x squared dx. And in for dx goes this. And in for 1 plus x squared goes u. All right. So what's going to happen here is I'm going to have 2x times the square root of u times dx, which is du over 2x. And so now what happens is some magic, right? Because look, I have 2x over 1 right here, and then I have a 2x in the denominator here, and what's going to happen is these are going to cancel out, and I'm just left with the square root of u du. And now I'm in one variable, and this is a very simple function to integrate, right? Because this is u to the 1/2 du. So this is an indefinite integral, so I just use the rule that, we've been using. I add 1 to the exponent and divide by that number. Well, if I add 1 to 1/2, I'm just going to get 3 over 2. If I divide by 3 over 2, that's the same thing as multiplying by 2 over 3. And of course, since this is indefinite, I want to tack on that plus c right there. All right. And then here it is down here, which we're going to. Now, the last thing you want to do for these indefinite integrals is you want to go ahead and plug back in what u was originally. Remember, u was equal to this, 1 plus x squared. So I can plug that in here to give me a final answer of, so this is my final answer. This is my indefinite integral, and we found that by using substitution. So I'm going to do some more examples with you guys. So the trickiest part is always trying to see what I need to sub in for u. What does u equal? Well, 9 out of 10 times, as I said, you want to sort of, if you're within a function, you want to let u equal that. So what I mean by that is I see a cosine function and I see an argument of this. And I'm thinking to myself, wow, if that was gone, it would make this a whole lot simpler. Another way of thinking about this is think about, what can I take the derivative of that would potentially cancel out this x to the 3, right? That would potentially cancel out something. And so this part kind of takes practice, right? You're going to mess up, like maybe you could say, what if u is equal to cosine of x to the 4 plus 2? Well, then you say to yourself, okay, well, is this easy to differentiate? And the answer is, not really. It's not really going to be easy to differentiate, right? Because if we take the derivative of cosine of x to the 4 plus 2, we have to use the chain rule. So that's going to give us negative sine of x to the 4 plus 2 times the derivative of the inside, which is 4x cubed. And once we do the substitution for dx, we get a whole hot mess in the denominator, which is not going to cancel. So this was the wrong way of doing this. And you're going to find out that you're going to eventually notice, you're going to notice patterns, and you're going to get better at this as you do more of these problems. Again, I would recommend, if you want more practice with this, to look at the organic chemistry tutor, or there's textbook problems. And you can check your answers by looking at the odds. Now, I am going to give some problems like these on the study guide, maybe 6 or 7, but if you really want some more practice, these are some great resources. Okay. So what I'm going to do, so this is the hardest part, is figuring out what u could be. And you'll know it when you see it, right? So this is a good substitution. We're going to let u equal x to the 4 plus 2. Differentiating both sides and rearranging, I'm just doing this in one swift motion. I get du equals 4x to 3 dx. Now isolating dx, because that's what I want to sub in right here, isolating dx, if I divide both sides by 4x cubed, I get du over 4x cubed equals dx. And what's happening here is I made a good substitution. And why is that? Well, because if I put u back in here, I'm going to rewrite this. I get x to the 3 times the cosine of u times dx. Well, what is dx? Dx is this. Dx is the same thing as du over 4x to the 3. And now I get things that cancel. I get this cancels with that. And now I'm in one variable. So if you're in one variable, you know you made the right substitution. So what I'm going to do is, this is du over 4, which is the same thing as a fourth du. So I'm going to pull that 1/4 out, leaving everything else in on the inside. And now I know what this is, right? I can take, I can integrate this with respect to u. So this is basically saying, what do I have to take the derivative of to get cosine? And the answer is sine, right? So this is just going to be a 1/4 from the outside, sine of u plus c, right? And our last step is to plug in our original u, which was x to the 4 plus 2. So my final answer is 1/4 sine x to the 4 plus 2 plus c. That is my final answer here. All right, let's try this one. Again, I encourage you to pause the video and see if you can get the substitution right. That's honestly the hardest part here, I think. So what I'm going to do is I'm going to say, well, I have something under the radical. That's probably what u is going to equal. So what I'm going to do is I'm going to let u equal 2x plus 1. Therefore, du is equal to 2 dx, taking the derivative of 2x plus 1. And from here, so I'm going to put this in my pocket and just kind of leave that. Well, actually, let's go ahead and isolate dx first. So dx is simply du over 2 if I divide both sides by 2. So I'll put that in my pocket. And let's go ahead and make my substitutions here and here. So this integral is going to become the square root of u. That's what I said 2x plus 1 was. And dx is being replaced by du over 2. Right? Now this du over 2, that is 1/2 times du, so I'm pulling the 1/2 out. And I get this. Now, I have a very simple function that I can integrate with respect to u. So remember, square root of u is the same thing as u to the 1/2. So when I integrate this thing, I'm going to get u to the 3/2 over 3/2, which is just times 2/3. All right, plus c. And if I simplify this out, I'm going to get 1/3 by multiplying these fractions, u to the 3/2 plus c. And my last thing to do is to sub in u. Well, we called u 2x plus 1, so I sub that back in. So my final answer is 1/3 times 2x plus 1 to the 3 over 2 plus c. That is my final answer here. All right, let's go ahead and do this one. So again, your strategy here is to see if you can take the complicated thing and set it equal to u and see if things will cancel out. So the complicated thing is usually the thing under the radical in this case. So I am going to see what happens when I let u equal 1 minus 4x squared. Well, my next step is to take the derivative. Therefore, du is equal to negative 8x dx. And I'm just, I'm skipping a step, right? Because what I did was I took the derivative with respect to x on both sides. So I got du dx is equal to negative 8x. And then I just multiplied both sides by dx to get what I have above. All right, so I just want to make that clear. Okay. So from here, if I isolate dx, I divide both sides by negative 8x. Dx is the same thing as du over negative 8x. So I can make that substitution. And I can make this substitution, and let's see what happens. So u is 1 minus 4x squared. So that's what I'm subbing in under the radical. And dx is the same thing as du over negative 8x. So that's what I'm subbing in here. Now look at what happens is I'm making this simpler because the x's cancel out. I can pull the negative 1 over 8 out. And so I'm just left with negative 1 over 8 over 1 square root of u du. And this is a simple function to integrate because this is the same thing as negative 1 over 8. Now, I can move this exponent to the top because the square root is just an exponent of 1/2. So this is the same thing as u to the negative 1/2 du. And from here, I can just, integrate how we usually do. And so what is this going to be? Well, that stays there. Then I have to add 1 to this exponent, giving me 1/2. Divide by 1/2. And maybe I'll just do this all out so you guys can see it. Plus c, of course. All right, so this is the same thing as negative 1 over 8 times 2 over 1 times u to the 1/2 plus c, right? Dividing by 1/2 is the same thing as multiplying by 2 over 1. And this simplifies, when I multiply these fractions together, that simplifies to negative 1 over 4 u to the 1/2 plus c. Well, u is 1 minus 4x squared. So my final answer is negative 1 over 4 times the square root of 1 minus 4x squared plus c. This is my final answer here. All right. So, the strategy again is kind of similar to when we're thinking about the chain rule, outer and inner functions. It's usually a good idea to let u equal the inner function. So what's the inner function here? Well, the outer function is e to the x, but what am I plugging in for x? Well, I'm plugging in 5x. So let's let u equal 5x. And if things aren't canceling, or if you're making it more complicated, you're doing it incorrectly or inefficiently. Maybe that's a better way of saying it. So if u is equal to 5x, then du is equal to, well, the derivative of 5x is just 5. So du is going to be 5 dx. And if I isolate dx, I just divide everybody by 5. I get du over 5 is equal to dx. Perfect. Okay, so now what should I do? Well, all I need to do is make my substitutions, right? And so u is equal to 5x, so I sub u in for there. So this is going to be e to the u, and dx is the same thing as du over 5, so I make that substitution. Now du over 5 is the same thing as a fifth times du, so I can just pull that 1 over 5 out, and I am left with this. All right, now we know that e to the x, or e to the u, is the derivative of itself. So when I take this indefinite integral, I'm just going to get e to the u. Now, and of course, plus c at the end. Now u, we said was 5x, so I plug it back in, and I get 1 over 5 e to the 5x plus c, and this is my final answer here. All right, let's go ahead and do this one. Now, this one is a little bit tricky. All right, so see what you can do here. Try to pause the video and see what you get. What I'm going to do is what I've been doing is I'm going to take that inner function in that f of g of x, and I'm going to let it equal u and see where I get from there. So I'm going to say u is equal to 1 plus x squared. Therefore, du is equal to 2x dx. Right? All right. So I'm going to make these substitutions. So what I get is I get the square root of u times x to the 5, and dx, if I divide both sides by 2x here in this equation, I get dx is equal to du over 2x. All right, fine. So that's going in here. And I can simplify these x's. So this is going to be, and the square root of u is just u to the 1/2. Now, so this is going to become x to the 4 times du over 2 when I simplify those in orange. I can bring the 1/2 to the front, and I just get this. So far, so good. Now, there's a problem. The problem is that this is not in terms of u. I want to be in one variable before I differentiate, or before I integrate, rather. So the next thing you want to look at is, can I somehow write x to the 4th in terms of u? Well, let's go ahead and try to get this to have an x to the 4th in it by using algebra. So this is what we declared. We declared u is equal to 1 plus x squared. So what I'm going to do to get an x to the 4 into the equation is I'm going to first isolate x squared by subtracting 1 from both sides. And I can introduce x to the 4 by squaring both sides, right? That's going to give me x to the 4 on the right side. So I need to square both sides. And it turns out that x to the 4 is equal to u minus 1 squared. So I can make that substitution right here. All right, so now I get this, and I get times u minus 1 squared du. All right. I still can't integrate anything quite yet. So I'm going to have to, because I have a function times a function, and I can't, I can use the power rule and the product rule when I differentiate, but when I integrate, I can't do that. I need to have everything separated by pluses or minuses before I start integrating. What I can do, though, is I can FOIL this thing out. So let's do that off to the side. I'm just trying to make this look like a polynomial function, right? So when I FOIL this, I get u squared minus 1 is going to give me minus 2u. Minus 1 is a plus 1. All right, so let's go ahead and write that here. We got u to the 1/2 times, well, that's the same thing as u squared minus 2u plus 1 du. Okay? And from here, what I can do is I can distribute this guy in there. Let's do that. I know this is a pain, but it's okay. Now keep in mind, guys, when you multiply common bases, you keep the base and add the exponents. So 2 plus 1/2 for the first one is going to give me 5/2. The second one, we have minus 2 u to the first times u to the 1/2. We keep the base u and add the exponents to give me minus 2u to the 3/2. And finally, for the last one, we just get plus u to the 1/2, multiplying u to the 1/2 by 1. So now we're all separated by pluses and minuses, so we can go ahead and integrate this guy. All right, so on the outside, I have this 1/2 still. Now, u to the 5/2, if I add 1 to the exponent, I get u to the 7/2 over 7/2, which is the same thing as times 2/7. And this is pretty ugly. It's all right. All right, oops. On to the next one. Negative, wait, this is, I forgot my u here. Minus 2u to the 3/2. If I add 1 to 3/2, what do I get? Well, I get negative u to the 5/2 over 5/2. Well, I'm going to do this off to the side. I have 2 over 5/2. So this is 2 times 2 over 5, which is just 4 over 5. All right, so I'm going to rewrite this as with this 4 over 5 in the front to make it look a little bit less ugly. And then finally, if I add 1 to this exponent, I get u to the 3/2 over 3/2, which is the same thing as multiplying by 2/3. And of course, I have this plus c at the end. Now I can distribute this 1/2 to everybody. And this is just fraction multiplication from here. So this is going to give me a 7th u to the 7/2 minus 2/5 u to the 5/2 plus a 1/3 u to the 3/2. So again, I just distributed that 1/2 in plus c. And last thing to do is to sub in my original u, and u was 1 plus x squared. So let's do that. And this is my final answer. All right, let's go ahead and do this. So what is there to do here? Well, there's really nothing. I mean, let u, like your natural instinct might be let u equal tangent of x, right? Well, then du is equal to the derivative of tangent of x. And the point is that this is going to be ugly and nothing's canceling out when we take the derivative of tangent of x. It's one of those special derivatives. So what we need to do is we need to use our knowledge of our trigonometric identities to make a substitution here before we make a u substitution. So from trig, we know that tangent is equal to sine over cosine. All right? So before I do any kind of u substitution, I'm going to say that tangent is the same thing as sine over cosine. And here we are. What we're going to do is we're going to let u equal cosine of x. And again, I encourage you to mess around with this and try, I'm doing it the quote-unquote correct way here, but I want you to see that if you let u equal sine of x instead, then you're going to be stuck, right? Because if we said let u, this is fake. This is not how we really do it. But for someone that doesn't, or for someone that hasn't been doing calculus for a while, like you guys, it might not be as obvious at first. So if we let u equal sine of x, and actually I probably did this too when I was first looking at this problem a few weeks ago. Pretty sure I did this. So, and it's just about messing around, right? So if we let u equal sine of x, well, then du is going to equal, well, the derivative of sine is cosine. Then we isolate dx, and we get dx equals du over cosine. So let's get rid of the real one here. So if we make these substitutions in our integral, then we get u over cosine times du over cosine. And we're at a standstill because we're still in terms of x. On the bottom we have cosine squared, and on the top we have u. So this is not getting us anywhere with that substitution. So then you say, okay, well, it's not sine, so let's try cosine. Let's try letting u equal cosine of x. So that was the fake one. And this is the real one. This, I think, is going to work. When we do that, we get du, differentiating, we get du. Well, the derivative of cosine is negative sine of x. Right? Taking the derivative of both sides. Now, if we isolate dx, we get dx equals du over negative sine of x. And aha, I think this is going to work, right? Because if we make these substitutions that I boxed, what we get is we get sine x over u. Dx is the same thing as du over minus sine of x. And eureka, these sine of x's cancel, which is what we wanted. So let's pull this back down here. All right. So now what we have so far is we have 1 over u times du over negative 1. I'm going to pull that negative 1 out in the front. So remember, this was one of those special integrals that we talked about. Now, the antiderivative of 1 over u is just going to be the absolute value, or sorry, ln of the absolute value of u. So this is going to be negative ln of u plus c. That's our answer here. Now, u, we said, was cosine of x, right? So our last step is to sub in cosine of x in for u. And this is our final answer here. Okay, I'm going to go ahead and stop this video, and we will do these last few in the next video. Thanks for watching. Hey guys, in the last video we talked about using u substitution to evaluate indefinite integrals. And now we're going to talk about using u substitution to evaluate definite integrals. All right. So definite integrals, again, is when you have defined bounds for the integral. So For example, here we have a lower bound of 0 and an upper bound of 4. That is where we're integrating this function. That's where, we're finding the area under the curve from x equals 0 to x equals 4. All right, so let's talk about doing this. So the first thing, we're going to do is we can't integrate this off the cuff because we have, an f of g of x situation where we have an inner function of 2x plus 1 inside of an outer function, quote unquote, of square root of x. And so what I'm going to do is I'm going to say that we're going to let u equal 2x plus 1. Therefore, du is equal to taking the derivative of 2x plus 1. Du is just going to be 2 dx. All right. Isolating dx, we get dx is equal to du over 2. So that is what I need to do first. I got this substitution. I get this substitution. But what we need to do now is we need to change these bounds, right? Because I'm no longer integrating with respect to x. Once I plug this stuff in, I'm going to be integrating with respect to u. So, I'm no longer integrating on these bounds from 0 to 4. What I need to do is let me write this down. Need to find new bounds, upper and lower bounds, because we are no longer integrating with respect to x, but with respect to u. Okay, so how do I find the new bounds? Well, I'm going to use this equality. U is equal to 2x plus 1. We started, so the starting bound is at x equals 0, right? That's our lower bound. And so I'm just going to plug in 0 here to see what that corresponding u value will be. Well, that's just going to be u is equal to 2 times 0 plus 1, which is going to give us 1. So this is my new lower bound. Now what I need to do is I need to find the upper bound. Well, my old upper bound was going from, until x equals 4. So we are ending, our upper is at x equals 4. Therefore, our new upper bound, we're going to just replace 4 in for x to get this in terms of u. So u is going to be 2 times 4, 8, plus 1 is going to give us 9. So this is our new upper bound. All right, so putting all this together, we are going from 1 to 9. Those are our new bounds. And in terms of u, we have the square root of u, right? We have the square root of u times, well, dx is no longer dx, but dx is the same thing as du over 2. Right? Now I can pull out the 1 over 2. And now I can just integrate this thing like I would do. So the square root of u is the same thing as u to the 1/2. So what I have is this 1/2 on the outside. Then using the fundamental theorem of calculus, I have u to the 3/2 over 3/2, which is the same thing as times 2/3, from 1 to 9. And maybe I made this bracket a little too far away. So using the fundamental theorem of calculus, this is going to be 1/2 times 2/3, 9 to the 3/2, plugging in 9, minus 2/3 times 1 to the 3 over 2. All right, so this is by the fundamental theorem of calculus. I have that 1/2 on the outside. On the inside, I'm going to end up getting 18 for this piece, I believe. Let's see. Yeah. Minus 2/3 for that second piece. And when I simplify this out, 1/2 times 18 minus 2/3, I end up getting 26 over 3 as my final answer. All right, let's do another one. So again, I have a definite integral. So I'm going to, before I integrate, I want to make sure my bounds are changed after I do my substitutions. So let's go ahead and the most complicated thing, f of g, our inner function in this case is going to be 3 minus 5x. And so what I'm going to do is I'm going to say let u equal 3 minus 5x. Therefore, du, when I take the derivative of 3 minus 5x, is just negative 5 dx. Isolating dx, I get dx is equal to du over negative 5. So I know I'm going to sub in these two things. But before I do that, let's go ahead and find my new bounds. My old bounds are in terms of x. X goes from 1 to 2. But I want to find my bounds in terms of u, since that's what I'll be integrating with respect to. So I need to use this guy. So u is going to equal 3 minus 5 times 1 for the lower bound. So u is going to be negative 2 for the lower bound. And u is going to be 3 minus 5 times 2 for the upper bound. So this is going to give us negative 7. So this is my upper. And now that I have all of that, I can just plug it in place of my lower. Instead of putting 1, I'm putting negative 2. That's my new bound since I'm integrating with respect to u. And my upper is going to be negative 7. Now dx, we know, is going to be du over negative 5. So I'll just pull that over here. And then on the bottom, I have 3 minus 5x, we let be u. All right, so this is what I have so far. Now what I can do is I can pull out the negative 1 over 5. Since it's a constant. And I just get 1 over u squared du, or du over u squared if you like that better. Now what I'm going to do is I'm going to rewrite this to not have a denominator because I don't like denominators when I integrate. This is the same thing as u to the negative 2 du. All right, now I need to start the integration process. So I'm going to use the fundamental theorem of calculus to do this. I'm going to pull this negative 1/5 out, and I'm going to do my, I'm going to add 1 to the exponent, which is going to give me u to the negative 1 over negative 1. And by the fundamental theorem of calculus, I'm going from negative 2 to negative 7. Okay? Let's go ahead and do the subtraction. What do I have? Well, my upper bound is negative 7, so I'm plugging that in for u. I have negative 7 to the negative 1 over negative 1 minus, now I'm plugging in negative 2 for u. All right, that's by the fundamental theorem of calculus. And when I compute this all out, I get a final answer of 1 over 14. So this is my final answer right there. All right, let's go ahead and try this one. So again, I have a definite integral because I have an upper and lower bound here. My lower bound is 1, my upper bound is e. And what I'm going to go ahead and do is I am going to let u equal ln of x. And again, if these substitutions aren't completely obvious to you, it's okay, that's normal. it really does take practice, all right? Because when you make a wrong substitution, you're going to see that things aren't canceling and it's not getting simpler. But when you do a right substitution, it will get simpler. All right, so there's u. U is equal to ln of x. Therefore, du, well, the derivative of ln of x, if you recall, is 1 over x. And we'll tack on that dx. If I solve for dx, I multiply both sides by x, and I get x times du is equal to dx. So I have this guy that I'm subbing in and this guy. And what I need to do is I need to change my bounds before I put that back in to solve. So to change my bounds, I need to use this relationship that u is equal to ln of x. So my lower bound is this one, right? And so I have ln of 1, which is just equal to 0. So my lower bound is now 0. My upper bound is changing to ln of e, which is just 1, right? ln and e are inverse operations. So now I can change the bounds here. I'm going from 0 to 1, and ln of x is equal to u. So that's going to be u over x, and dx is the same thing as x times du. And this is the point where you say, oh, I did this right, because the x's cancel out, and now you're just in terms of u. All right, so I have 0 to 1, u du. So what does this turn into? Well, this is just going to be u squared over 2 from 0 to 1. And by the fundamental theorem of calculus, I plug in 1 for u minus plug in 0 for u, and I end up getting a final answer of 1 over 2. All right, well, that is all I have for today. Thanks for watching, and I'll see you guys next time.